So this is the Academy for Science and Design's Modeling Substance Use and Abuse Solution presentation. So even though the M3 challenge is a mathematics competition, we like to look at the challenge this year in a broader theme and look at its applications in the real world. We noticed that all three of the problems really stress the idea of the growth of illegal drug use of the youth in schools. And we also noticed that the solutions to these problems in the challenge showed that the growth of illegal drug use would continue as long as there are friends present to influence their peers. So the first part of the challenge is, we call it the Darth Vapor, and we said it was asking us to create a mathematical model to predict the spread of nicotine through e-vapes or e-cigarettes in the next 10 years. So to start off, we made some local assumptions or some assumptions for the specific problem in order to serve as guidelines for our mathematical model. The first assumption was that only youth and young adults will be considered for this model. We provided this idea due to the fact that there's a really small number of adults that actually use e-cigarettes, and they only use them in replacement for their traditional cigarettes. Another assumption we made was that the problem statement asked us for the next 10 years to make a prediction, and we interpreted this from 2019 inclusive to 2029. So these are the variables and constants for our mathematical model that I will show in the next slide. You can see that we have K, P initial, R, and T, and they are carrying capacity, initial population, rate of growth, and time, all respectively. So you might have already seen the K, or carrying capacity, and that might bring you to the idea that we used a logistic model for our mathematical model for our prediction. We chose the logistic model due to two main factors that we liked. One was that it's exponential growth in the beginning. We thought that as more friends use e-cigarettes, they're gonna spread their influence to other friends, and this will continue to grow. We also like the idea of a limiting carrying capacity because we believe that it's not exponential. There's no way that we're ever going to reach 100% of high school students using e-cigarettes. So we wanted a limiting carrying capacity. And to find the mathematical model and the values, we use actually MATLAB's curve fitting tool, and we fit data from high school students who use e-cigarettes from 2011 to 2015, and we got these values and this function above. So the second part of the question asks us to compare the e-cigarette growth to the growth of cigarettes. And if you look at the left graph, we actually have a graph of cigarette growth for 8th, 10th, and 12th graders generated by MATLAB again. And we got this data from the U.S. Department of Health and Human Services. A quick glance at it, we already noticed a lot of comparisons and a lot of differences. For the logistic model, we saw that it grew exponentially. That's what our model predicted. But the cigarette growth was really steadily with time. And then another big difference was that cigarette growth really declined in the 1999s, around there. I think that's when people started to realize that cigarettes are actually not good for you. But our logistic model predicts that it will reach a carrying capacity instead of declining. So we had to validate our model to make sure that it was robust and that it was valid. And we compared our prediction made for high school students using e-cigarettes in 2018 with information given by the CDC. And we did a percent error analysis or calculation, and we saw that the percent error was a low 12.1%. We also did a sensitivity analysis, so we arranged the values plus or minus 10%, and we found that our model is actually robust in the presence of uncertainty. So there are a couple strengths and weaknesses on our model. One strength that we really enjoyed was its simplicity. This was due to the fact that there's only one input, the year since 2011, and there's one output, and that's the percentage, which is essentially what we wanted. A weakness is probably the accountability for events. So let's say the government made a new regulation that limited e-cigarette usage for high school students. We can't account for that in our model, and that's a weakness that we have. Another weakness is probably the low sample size. Due to the fact that the rise of e-cigarettes was really new, we didn't have a lot of data on it, and we believe that a larger sample size would provide us with a more accurate model.
Part two, above or below the influence. So to begin, we created local assumptions. So students are randomly distributed into social circles, each containing 6 students. And we also ignored overdose mortality, as it is low enough to be ignored. And each substance is independent, so usage of one substance will not affect the usage of another substance. And in our model, we assumed that that race and quality of living and other factors are correlated or may be correlated to income level, and due to lack of data, we did not consider these factors. Our mathematical model contains 2 major parts. The average drug use % increase per year, which is calculated by summing all our factors, which in this case is income levels and gender, and dividing it by the amount of factors. Our second term is how likely your friends will affect you, and this is calculated by how likely a single friend will affect you on a certain drug times the amount of addicted friends you have. So combining these 2 terms with 1/12, we get the likelihood that your friends will, likelihood you will be addicted to a substance per month.
All right, so when utilizing this model, this just gives us one step for when a friend can be addicted or become addicted from one set of friends. However, we felt that it was important to treat this model as a dynamic situation and use a simulation to model this. This is because we wanted to model the ever-changing nature of social circles and friend groups, and the fact that drug use and abuse can potentially spread through these friend groups. So to do this, we developed a dynamic simulation that treats the senior class as essentially a weighted graph. The nodes of the graph are people in the class, the edges are friendships and relationships, and the weighting between the edges is the ease of influence across those friendships to use a certain drug. In order to do this, we use tools such as Python, NumPy, and Jupyter notebooks. So to go into a bit more detail about how we actually achieved this, we began by generating a random class of 300 high school seniors. To do this, we randomly initialized factors including gender and income, and this allowed us to get a class. We would then run the simulation step, as shown in the previous slides, repeatedly for 24-month-long periods. The reason we needed to use 24 periods is because our initial data began at the end of sophomore year, and so we needed to go for 2 years, or 24 months, to reach the end of senior year and determine a percentage by then. Finally, we'd run this simulation on numerous schools and senior classes, eventually coming out with an average that we would be able to use as our value. So here's just some sample output from the code we wrote. As you can see, the left-hand side will give us values for the number of students using a certain substance at the end of each individual month. And then on the other side, you can see that we're then running this simulation repeatedly on various schools in order to get averages that are, in theory, more precise. So here are some example results of looking at how this model predicts spread of drug use over time. Now, one thing that we found interesting about this particular graph is that it starts off very flat. These initial points, especially before around 5 months, are very flat, and then over time it begins to get steeper. This led us to postulate that we might actually be looking at another logistic model here, and the only reason that we haven't seen it reach a carrying capacity yet is because at the end of that 24-month period, at the end of senior year, there was just no more time for it to reach that carrying capacity. So in theory, if we were able to continue this simulation through more years of school, we might see this reach a similar logistic function as we saw in part 1. Now, as far as validity goes, our model gave us surprisingly good results, and we were very happy with them. All of the 4% errors for the 4 substances involved in this simulation all gave us percent errors of 15% or less with respect to data from the National Institute of Health. This was really important because it meant that we had utilized these variables in a way that had actually given us valid results, which we were really happy with. So to move on to the strengths and weaknesses of this, the main part is of course the fact that we were able to utilize a dynamic simulation and utilize our programming skills in order to look at this in a way that's very time dependent. Rather than just using a static equation that took in values about a student and gave out a percentage chance for them to use a certain substance, we were able to actually look at the big picture and see how this would change over time. The simulation is also extremely modular. If you look at the tobacco metrics line underneath there, if we found more factors that could potentially influence drug use, we could easily add them into this line, and the simulation would continue to work without any additional modifications. So more data doesn't make this harder to use. Weaknesses, of course, were that there wasn't very much data to use, and unfortunately we were only able to find usable data for gender and income, and also the fact that the variables are coupled in a way that we might not have taken into account. Some correlations between the variables might be overused. However, for the most part, the model does give really good results, and we were really happy with it. Thanks.
Part 3. Ripples. Drugs are universally accepted to be dangerous, but we still do not have a good way of telling exactly how much worse one drug is than another. Money can go down the drain fast, while relationships and health can be ruined. Developing a numeric metric is important because it gives us a smooth measurement to compare the effects of drugs on different people. We made 3 assumptions here. Death is the most costly outcome to any person, that's one assumption. Second, we considered it that, we discounted the case where the expense goes beyond the income and the drug abuse cannot be sustained by legal means only. The third is that we considered that each individual case can be considered in isolation. We used 2 parameters in our model. The money lost from drugs and the lost life expectancy. Here, we did not include certain costs such as hospital bills because they are very hard to predict. So those sorts of costs are very difficult to predict in general. And also every scale, all of our scores use a scale from 0 to 100.
So this table shows the variables involved with our model. It is important to note that our original health damage model in our original paper actually had a significant typo. Also, we found an equivalent form of our whole model where the health and financial damage scores were independent. And we updated the models here to reflect those issues. So first off, the financial damage score is what percentage of your total income is put towards drugs. And the health damage score is what percentage of your total life expectancy was lost due to the use of drugs. The equation for the total substance damage is identical to the probability OR function, combining both factors in a similar fashion. So a score of 0 means that there's no damage at all, while a 100 in either category indicates critical danger. These graphs show the substance damage scores for a 20-year-old with a annual income of $20,000 and a normal life expectancy of 76.7 years. The left uses the financial and health damage scores, while the right uses the total life expectancy and money spent on drugs. These graphs illustrate how the various research drugs, their substance damage scores do not exceed 60 at worst, even for a person with a low income. This is a 3-dimensional version of the previous graphs. It shows the relative risks of the various drugs through the peaks of each bars. And these graphs were all generated with MATLAB.
This table shows the data we found alongside the results from our models. Notably, vaping is the least dangerous from all of the drugs that we tested on, having the lowest life expectancy reduction by a small margin, and a very low cost for a drug, $700 per year. Opioids reduce life expectancy by more than cigarettes do, but cigarettes cost almost $7,000, which is double that of prescription opioids. This is probably why the cigarettes have the higher substance damage score. And alcohol has a pretty high annual cost of $4,500 and a very high life expectancy reduction of 26 years. This explains why substance damage score is the highest out of them all. This model is simple, and yet it allows us to really easily compare the different impacts on drugs with different people of different ages and different incomes. Like between a 20-year-old who earns $20,000 a year and a 25-year-old who earns $40,000 a year, for example, each using their own types of drugs. We get to use these scores to Each of these scores can also be validated by using test data. Even in its simplicity, this model really works for any data input, such that the scores all fit between 0 and 100. And that was the reason why at the beginning we made the assumption that the expense of the drug does not exceed the income. We lack accounting for medical expenses from drug abuse and other essential costs like food, rent, and taxes in this model. We also don't have a really good breakdown of the score threat levels. Given more time, we could have done something like created boundaries for the score ranges to categorize into low danger, medium danger, and high danger. And the biggest issue with this model is the fact that it's rigid. We have no coefficients and it's completely symmetric. One way to fix this issue would probably be to make a new model which uses coefficients and fit it to our own definitions of exactly how much each parameter impacts the drug addict. Of course, this would require an in-depth understanding of how much each parameter impacts the drug addict.
So our conclusion, we'd just like to thank all the M3 judges and all the coordinators for allowing this event to happen. Thank you.
I want to start. I'll ask you about question 1. It looks like you built your model so that it would match the data at the initial value, t equals 2001. Is there a reason why that data point was so important, that it was important that your model fit exactly through that point?
So our data was actually fit from, I think, the start of 2011, and we never chose that point specifically as, per se, the starting point. I think that was just what MATLAB chose when we used the curve fitting tool, and that's how it just fit it.
Additionally, that was our first data point, so that's another reason why that is.
Okay, so let me ask you this about question 3. So you specifically mentioned that your results have a specific assumption that the person is 20 years old with a specific annual income, and this is out of your paper. And you had cited a source, and I went to that link to try to understand the connection. So you had said the results assume the person is 20 years old with an annual income of $20,000, with a specific life expectancy as someone born in 1999. Can you elaborate on that assumption and just explain to me why it was there or how your model applied it? How would your model apply to any individual?
To apply to any individual, you would probably have, the thing you want to find is how much their expected life length, the expected life length, and what else you would have to find. And we consider the relative income, relative cost of the drug. The cost of the drug relative to the income is our danger level in a percentage form. And also the amount of life expectancy reduction relative to the normal life expectancy left. That is our other danger factor.
Okay, so let me just clarify, but the results that you presented were based on those assumptions? Was some of the data that you collected based on that particular individual?
Oh, it's not really based on the exact individual. Those are actually calculated from those basic assumptions, like a 76.7 year life expectancy. It was just for an example person, for some example of a person, just because we needed some concrete values. It's just an example. You can apply it to a 40-year-old, an 80-year-old, and you can apply it to someone who has a 20,000 income or 200,000 income.
I'd like to go back on page 15 of your presentation. You were talking about simulating interactions between people, and you're talking about the edge weights corresponding to transmission rates between people. As you step through your simulation, did you recalculate the edge weights?
All right, so these edge weights are calculated from factors relating to the individual person's, factors such as gender and income. These are static across the model, which is potentially one of its pitfalls. However, the way that we thought of it was that each person had a certain susceptibility to use each certain drug, and based on this susceptibility, that would be their ability to be influenced.
And how did you calculate those edge weights?
So the influence rates, the edge weights, we calculated by finding the percentage of people that were affected by a substance due to peers over the sample size, which is just how many people that didn't use the substance, and those two divided by each other gives us the influence rate, which is edge weights.
So this essentially was going to give us the probability of transmission of drug use from one person to a friend.
Okay, thank you. Yeah, I'm gonna conclude with the question.
Thanks. You guys can head out.